And Lara, do you want to share your screen? Just get things set up while that wraps up. Great. So thanks everybody for being here. I guess I'm moderating this next session, and Lara Anderson is the next speaker. She'll tell us about progress in string compactification. So Lara, I'll give you a heads up 5 minutes before your 25 minutes is up. So please take it away.
Thank you very much. Thanks also to the organizers for putting together a really interesting roster of talks, both last week and this week. And thanks to everybody for hanging in there late in the afternoon. I know this is a lot of things to listen to in one day. So I'm going to be talking about the subject of string compactification. And in particular, I'm going to talk about two papers that were completed recently in collaboration with James Gray at Virginia Tech. The first one with Magdalena Lefors, Matt McGill, and Robin Schneider, all at Uppsala. This was a project that was done while Matt and Robin were visiting students at Virginia Tech and proved to be a fruitful visit. And then I'll also be talking about work done with James, Mattis Curtis, Sven Krippendorf at LMU, Nikhil Raghuram, who's our postdoc at VT, and Fabian Rula at CERN. So to begin, I'd like to start with a little bit of quite general motivation, which is we've heard about lots of different limits of string theory, lots of different effective theories that are obtainable from string theory through different approximations in different dimensions. The process of beginning with 10D string theories and trying to get down to particular, for example, 4-dimensional effective theories is one with a history dating back to the start of string theory, and it is continued over the last 30 years to be a challenging one. So in general, if we begin with some higher dimensional string theory, we need to reduce on compact geometry to obtain 4D physics. And the question is, how does one actually practically do that? So you need a tremendous amount of technology to actually push the effective field theory down to the level of detail that you'd really like to be able to decide, is this useful, for example, for the 4D universe that we seem to live in? So here I put on my slides, for example, can you calculate the mass of the electron in a string vacuum? That's already come up in this conference as perhaps an overambitious hope in the early days of string theory. So the goal of my talk today is not to say that we can calculate the mass of the electron in some fully stable ideal string vacuum, but rather in any string compactification, how do you actually get out a number, even if it's wrong? What are the rules that one would want to impose on the geometries that you want to study, rules for top-down model building, patterns, constraints, and predictions? So in general, as we know, there's truly a vast number of different compactification geometries that might be considered, but the question of which ones you care about is an extremely difficult one. Whether there is 10 to the 500 or perhaps an infinite number of string vacua in some corner where none of those theories have an electron, maybe that's a different question or a question that you aren't so interested in answering. What you want to understand is something in this Venn diagram. If you have some field theories of interest, here I highlighted string Vino, but this could be any theories, gravitational or gauge, with properties you're interested in. The question is, how do you understand what subset of string dimensional reductions can actually lead to the physics you're interested in? And of course, that's an incredibly complex question where we replaced which of possible effective field theories with which geometries in general. So this is a broad set of problems and aims to be solved, but I want to highlight a few of these effects today in the context of n=1 4-dimensional compactifications of the E8 cross E8 10D heterotic string, just to illustrate how one might try and gain some traction both on these large-scale questions about general constraints and patterns, as well as how do you push the theory as far as possible. So to begin, I'm going to talk about one particular feature of a 4-dimensional heterotic compactification, which is the trilinear Yukawa couplings that arise in the superpotential. So as a very broad strokes, in the background of a heterotic theory, we have some compactification manifold, say 6-dimensional, and a holomorphic vector bundle over it. And in terms of that background data for the theory, we can perturbatively define the 4-dimensional theory and fluctuations around that background. Here I've defined a gauge field in the compact extra directions, i.e. x, and fluctuating around some initial value of that connection, you have what are going to now be 4D matter fields phi that are expanded in a basis of harmonic 1 forms over the compactification manifold. It's well established then that if you ask how do those fields couple to one another via the superpotential, then the trilinear couplings have a simple form in terms of integrals of these harmonic forms over the background manifold. I'm going to start saying Calabi-Yau here is the simplest class of geometries, but we'll broaden that out later in the talk. So for example, a Calabi-Yau background, we have an integral of 3 harmonic forms wedged together with a holomorphic 3-knot form. And in principle, this gives you the coefficients of the trilinear couplings. Now, in any given theory, as I said, we're interested in particular structure. So as examples, in the standard model, for example, we know there's a heavy top quark. So you ask, can I have hierarchies of masses? In supersymmetric theories, famous problems like the mu problem, how do you forbid stuff that's allowed by gauge invariance, forbidding rapid proton decay operators? There's a lot of structure for these couplings that one wants to consider. Of course, this is just the superpotential in the supersymmetric theory. If we were actually doing a realistic vacuum, we've got to run this down to lower energies, break supersymmetry, a bunch of other things will happen. But if you can't control this supersymmetric data, then you don't have much hope of controlling anything else. So here's the topic that I want to explore today. In general, if you take a heterotic theory out of a hat, what you find is that you need to be able to compute these couplings effectively, and you want to say something about general structure of all possible heterotic compactifications. And one observation that you can make quite rapidly in particular examples is that heterotic theories tend to exhibit so-called topological vanishings. That is, if you actually calculate these numbers in a given background, what you find is that there are many more couplings that are forced to be 0 by the choice of compactification geometry than you would expect due to gauge invariance of the theory. So the question that my collaborators from Uppsala and at Virginia Tech and I set out to understand is what geometric effects in the background can lead to these topological vanishings? How do these effects differ? Can they be related? How generic are they? And can these be explained by some sort of hidden symmetry of the theory? So first, I have to tell you a little bit more about these numbers, actually computing superpotential couplings and what goes into that. So how do you actually compute the numbers? Well, the earliest examples that were explored in the literature were Yukawa couplings for so-called standard embeddings of heterotic string theory, in which the gauge bundle and the tangent bundle were chosen to be the same. In these, you have a lot of the power of 2-2 theories instead of 0-2 theories, and you can use mirror symmetry to interpret these numbers as some statement in the dual geometry or mirror geometry, particularly triple intersection numbers in the mirror. However, in general, you have no such in for these numbers. And very early on in the late 80s, early 90s, it was discovered that you could reformulate this question as one essentially of polynomial multiplication. So the integral formulation of these harmonic forms that I mentioned previously can be rephrased as a cup/Uneta product in cohomology, in which you're mapping bundle-valued 1 forms of the following type. Now, I've written an expression in terms of harmonic forms. I've now generalized this to a general closed form, but these numbers will differ by a closed piece and can drop out of the integral. So up to overall normalization, which is important and we'll return to, we can say something about the structure of these numbers based on such trilinear products. And basically, there's a lot of cool tools for taking a bundle-valued cohomology group and transforming it into a problem in polynomial multiplication, i.e. Grosvenor basis calculations. So this is intensive, but possible, and you can tackle various problems computationally, and people over the last 15 years have done so, including myself in various contexts. More recently, also different groups were interested in returning to the sort of differential geometry origin of this problem. And in particular, they were interested in looking at simple manifolds defined, Blesniak and collaborators, this was Blesniak, Bookbinder, Candelas, and Lucas, were interested in computing these couplings in heterotic backgrounds defined as complete intersections in products of projective spaces. This could be generalized readily to toric varieties, but this was the simple initial class that they were considering. And what they found is that if you have a simple description of your compactification manifold in terms of some ambient space, then you can effectively, in simple cases, pull back this integral problem to one that is simply defined over that ambient space. Now, the point of this is that you can take forms that are closed on the Calabi-Yau and pull them back to not necessarily closed forms over the ambient space. And here the holomorphic 3 form has a very simple relationship to a delta function current that allows you to actually transform this integral into one that is quite tractable in structure. And the interesting thing is, for simple ambient spaces, you can see structurally that many couplings have to be 0 simply by the form of the ambient space. So as a simple sort of toy bit of intuition, if you have an ambient space that has small dimensional factors in the product, later we'll talk about this in the context of blowups or other things. For example, if you had a P1 factor, you can see that you can only stick sort of so many legs of a differential form into that direction before this must be forced to be 0. So a simple form for the ambient space can affect the form of these trilinear couplings. In this formalism, it's easy to see that some things must be 0, and this is using an ambient space to obtain information of that type. So what my collaborators and I set out to do was to try and understand, can we phrase that in a bit more generality, the types of observations that was just made using differential geometry. And we proved a number of theorems in a recent paper. I'm just going to give one as a rough bit of a flavor for the idea here. We found that the tools of homological algebra, which in general, one should not show one's algebra in talks, including homological algebra, but I will say briefly, the tools of homological algebra allow you to get nice information about the structure of these unita products or trilinear products in cohomology very readily from specific descriptions of the bundle in which your forms are valued. That description can involve an ambient space, like the differential geometry approach I just mentioned, or it can be much more general. So in general, what we said is, given any resolution of a bundle, this is a description of your simple bundle over the Calabi-Yau in terms of some data, possibly bundles on an ambient space, possible simpler sheaves, line bundles, abelian gauge fields, anything that's giving you easy information about this. If you can package your bundle in terms of a resolution, then we can filter the bundle valued one forms according to the data of that resolution. And specifically, we can come up with vanishing criteria based on the dimensions of cohomology of objects in the resolution, which will tell you which couplings, i.e. which forms living in the bundle valued cohomology can consistently couple to one another. So this is a notion of type, which was generalizing the work of Bookbinder, Candelas, and Lucas, and we come up with some vanishing criteria. In this framework, you can easily see that the differential approach that was obtained previously can be described in terms of a causal resolution of the bundle. So this is describing a vector bundle in terms of a resolution where the curly data here is defined over some ambient space and then is restricted to a Calabi-Yau. My goal today is not to get into the details of this theorem or how we proved it, but rather to point out that there's interesting structure that can be described quite generally about heterotic theories in this context. So in general, this is one example. I gave you a description in terms of an ambient space where you can say something about whether the trilinear couplings must be zero or not. There are several other effects known. This is not necessarily exhaustive, but several other geometric effects that can force topological vanishing, couplings to be zero that you didn't necessarily know were going to be. Broadly, these can arise either from the manifold. So I gave the example of a simple ambient space as one. Two other effects involve another description of the Calabi-Yau manifold as, for example, as a fibration. And this has dated again for the last 15 years. For manifolds that emit fibration structures, it was well understood that this imposes strong constraints on bundle-valued cohomology and their possible couplings. And we also have data involving the so-called Mumford slope stability of the bundle and Kähler-Kohn substructure. I won't get into the details of this, but simply to say that the vector bundles have to satisfy non-trivial equations of motion, just like the Ricci flatness of Calabi-Yau manifolds. And their ability to satisfy that can lead to massive symmetries that can have an effect in terms of constraining the possible couplings in the theory. What we showed in our paper is that homological algebra tools can also be used to describe these other effects as well. So you have an in for calculating broad classes of topological vanishings. Now, the next question you ask is, who cares, right? Can you actually see some structure? Does this tell you anything about what classes of theories you might want to write down or what types of geometries might be of interest to you? So the first question you can ask is, given diverse geometric origins for topological vanishings, if I have, say, constraints on the couplings due to the description of the manifold in some ambient space or to its description as a fibration, will I get the same data from different geometric origins, the same topological vanishings from different descriptions? And the answer, we explored this in various contexts, is a definitive no. So in general, each distinct description of a geometry can impose different couplings to vanish. And of course, if any one description tells you it's zero, since it's the same theory in different descriptions, that's telling you that many more couplings are zero. So let me give a flavor of just one of those. I mentioned that the elliptic fibration structure or K3 fibration structure of the manifold will impose conditions on the couplings. It has recently been studied by many groups, including myself, James Gray, and our postdocs, Zhengao and Sanjuli, as well as Waddy Taylor and his student Huang, that Calabi-Yau threefolds are quite commonly fibered. So how commonly? One has to ask in different contexts, depending on the construction of Calabi-Yaus. But essentially, it is a true statement that almost all known or constructed Calabi-Yau threefolds emit fibration structures. So here is the famous Hodge number plot of Calabi-Yau threefolds. and a figure I stole from Waddy's paper, which was from some time ago. This has to be, it can be updated in much more detail now, of the number of Hodge numbers that correspond to fibered manifolds placed over the top. So observation, if you pick a Calabi-Yau manifold from the hat, odds are it's going to be fibered. Observation number 2 is that if you pick such a generic manifold, in general, we have found from many data sets, they do not admit just one elliptic fibration, they can admit many, order tens, hundreds, thousands, or in one case, actually an infinite number of distinct fibrations. Each of these distinct fibrations can induce topological vanishings of the type I'm mentioning, and the overall conclusion is that in any given description, you are going to have many, many constraints on the couplings. This is going to be extremely restrictive in general, probably too restrictive. So the sort of generic situation is that you will force nearly all of your couplings to be 0. Okay, so now let me change track for a minute and say, with that information in hand, what does Venn want to do? When you want to perhaps ask, can I use this general topological vanishing to eliminate large classes of theories that I might be interested in, or can I tune towards ones that might have coupling structure that could be relevant? For example, standard model type vacua with a heavy top quark. In that context, then, we need to be able to push the theory further. And with that, I want to turn to the second paper that I mentioned today, which is trying to determine the structure of the low energy potential in as much detail as possible. So I have glossed over in talking about superpotential couplings, I glossed over the fact that the technology as I described it to date could only talk about the couplings up to overall normalization. That is, the matter field Kähler potential for matter fields in heterotic theories is unknown except for very special cases. So structurally, the Yukawa couplings that I mentioned before, these will be derived from 10D terms in the 10D Lagrangian of this type. And crucially, the normalization and coefficients of these terms will depend on the metric over the compact directions, i.e. the Calabi-Yau background, and the choice of gauge connection over the Calabi-Yau. Also, I glossed over using harmonic forms versus general closed forms. Of course, the exact harmonic representatives are also metric dependent. The problem as well of pushing the theory to its limit, one of moduli stabilization, which we've heard lots about in various contexts in this conference already. Again, you may, in order to even find a stable vacuum, also need to know something about the structure of the geometry beyond just its topology. And that leads us to the question, how to determine the metric and connection. So in general, the only current totally general approach, especially for Calabi-Yau threefolds to this problem, is via numeric approximation. Now we're going to hear more about this in the next discussion session, but let me try and set the stage for that briefly. So the state of the art up until very recently is the so-called Donaldson algorithm to try and approximate a Calabi-Yau metric, a Ricci flat metric over a Calabi-Yau threefold. The idea is to use projective embeddings to try and generate simple metrics that can be parametrically tuned to a Ricci flat solution. So simple idea, given any projected manifold, i.e. a Calabi-Yau, we can use global sections of ample line bundles over that manifold to define the Kodaira embedding into some large projective space. The reason that this is an attractive thing to do is that projective spaces have very simple metrics, lots of isometries. The so-called Fubini-Studi metric is well understood as a Kähler metric on a projective space. And once you have a description of your manifold embedded into this simple ambient space, you can then try and restrict this metric down to your Calabi-Yau. Now, what you'll get will, of course, not be Ricci flat, but it is controllable. So in general, if we have a generalized Fubini-Studi metric generated by a choice of some ample line bundle in its global sections, we induce a Hermitian fiber metric on that line bundle over the Calabi-Yau. And it can be shown that the Kähler potentials that you would write down over the Calabi-Yau are in fact dense in the moduli space. And a theorem due to Donaldson, including his definition of a so-called balanced metric, provides a path in moduli space that can lead you to Ricci flatness. Specifically, he showed for each k greater than 1, where this is the twist of the line bundle, a balanced metric, which is not going to define here, but is defined as a fixed point of a T operator, which is iterating this fiber metric on the line bundle. This exists and is unique. As k goes to infinity, this sequence of metric actually converges to the unique Ricci flat metric for the given Kähler class and complex structure. Cool. So 15 odd years ago, various groups, including Mike, who will be leading the discussion session after this, actually worked on implementing this numerically and computing Ricci flat metrics numerically on Calabi-Yau manifolds. This is a computationally intensive task, as I learned when I worked on this some time ago as well. And the question you have to ask is, having generated a big numeric approximation to a Calabi-Yau metric in some particular case, is this accurate enough? The short answer is we don't know, because actually pushing this forward in terms of computing the metric, computing a connection, computing harmonic forms, and actually working out the terms in the 4D theory, for example, in heterotic that I mentioned, has not been run all the way to completion. In addition, moduli dependence of that metric is very difficult to obtain via the Donaldson algorithm. And this, although important in principle, in practice has not led to major new studies of field theories or vacua, simply because of the computational difficulty. So
about 5 more minutes.
Thank you very much. So I'd like to use my last 5 minutes to highlight a different approach to this using machine learning, which was done in collaboration with the people I mentioned earlier. And I'd especially like to flag the work of Fabian and Sven, who both have long programs on machine learning and are the real experts on the art of getting neural networks to do what you want. So we devised a series of goals. We wanted to study supervised learning of moduli dependence of Calabi-Yau metrics using the Donaldson algorithm to generate training data. We used direct learning of moduli dependent Calabi-Yau metrics, both using a metric ansatz such as the Donaldson algorithm and without it. And then perhaps the most significant, we studied the direct learning of metrics associated to SU3 structures with torsion. This is moving beyond the Calabi-Yau case and is the first time numerics of this type has been used in this context. And I'm going to give a brief flavor of these results. I should also mention that there were 2 papers that appeared in very close succession to ours, Douglas, with whom we coordinated, and Jajala shortly afterwards, who did similar things. So briefly, a definition of a Calabi-Yau threefold is as a complex threefold admitting a nowhere vanishing real 2 form and a complex 3 form that satisfy these identities on the top form and are both closed. The metric is related to the 2 form in the obvious way. And for the purposes of this talk, I'm going to be defining everything on the quintic hypersurface with a single complex structure parameter because it's easy to illustrate. So the first I'm going to discuss is direct learning of the Kähler potential. So the balanced metric output by Donaldson's algorithm at a fixed K is not necessarily the most accurate approximation to the Ricci flat metric. The first question, which is one of computational efficiency, is can a neural network do better? So in particular, we're going to use a basic feed-forward neural network, direct learning, to try and minimize the loss function, here designated as a loss sub MA, mange impair, which we are going to try and force the numeric solution towards the Ricci flat one. This is very similar in spirit to work done by Hedrick and Nassar, although we're obtaining moduli-dependent results and using machine learning rather than minimization functions in Mathematica. And what we find is that this actually works surprisingly well, or at least surprising to me. So here I'm showing 2 different results run over different ranges of the complex structure. The basic punchline is that what we find is that the neural network can produce results that are very comparable to Donaldson much, much quicker. So here, for example, this line is the Donaldson algorithm run at an accuracy of k equals 6. And the Donaldson algorithm, I should say, at k equals 12 takes order days or weeks to run, even for the single case of psi equals 0. This network at k equals 6 can take minutes and gives comparable accuracy for a whole range of psi. And we can do better than the Donaldson algorithm at k equals 6. This can be extrapolated. I should say here the shaded ranges are extrapolation in complex structure using these networks. Since I'm almost out of time, let me jump slightly ahead, which is to say that we attempted to direct learn the metric as well. So not using the Donaldson ansatz for the Kähler potential, but just directly learning the metric. The reason that this was useful is that it can be immediately generalized to non-Calabi-Yau cases. And again, this is the first time in the literature that we've been able to sort of distance ourselves numerically from the Kähler framework. The disadvantage of this is that you have to put in by hand, if you're learning the Calabi-Yau metric, that the thing is Kähler and that it's globally consistent. So we do this through the generation of loss functions of this type, where we have to impose the fact that the Kähler form is closed and overlap conditions to guarantee that this globally patches together correctly. What we find is that, again, this works reasonably well. So here we have the overall loss, which is trending downward for a direct learning of the Calabi-Yau metric. And we can play games with what happens if you turn off the Kähler condition or if you turn off the condition for global overlaps. And we find that if you turn off the Kähler condition, the overall error is bad, this doesn't work, but the solution is still trending downward towards something. So the question is, what is it converging towards? And with my last 1 minute, let me just say that the final experiment that we did was to try and learn SU3 structures. So we want to now move beyond the Calabi-Yau geometry. We want to consider situations where we again have a 2 form and a 3 form, but this time with different differential properties. So an SU3 structure can be classified by its torsion classes in this way. And these torsion classes parameterize how far off of closed forms you're running in this case. Specifically, we're interested in the context of the heterotic string theory. So we're looking for solutions to the Hall-Strominger system. Now, I'm out of time, so rather than going too far over, let me just say, instead of trying to generally solve for some mystery SU3 structure, we don't have existence theorems in this context, and we don't know about the global minima of the functions that we're attempting to optimize. So in this context, we decided to move towards a known analytic solution that was found by Larfors, Lucas, and Rula as an SU3 structure solution actually on a topological Calabi-Yau manifold. So although a Calabi-Yau can admit a Ricci flat metric, it can admit other non-Ricci flat solutions. And we used one of these to try and test the neural networks and see if it worked. So this is particularly important because such metrics have no analog of Yau's theorem. Again, we need to know that we're actually seeing something that isn't a numeric artifact. So let me just go straight to the result. We find, again, that this proves to be quite successful. Exactly how successful we can talk about in the context of the discussion session immediately after this. But what we find is that running this over the topological quintic, we can find that we converge to the known solution to high accuracy. And we can actually test this against the known solution point by point over the manifold and find a strong correspondence. So this, as from the point of view of the neural network, there is nothing special about the Kähler geometry that we're tied to initially in the Calabi-Yau case. We can generalize to non-Kähler very readily. The catch in this context, we considered the Strominger system because we are still using a lot of tools from complex geometry. And of course, it would be interesting to drop those as well. So since I'm out of time, let me try and summarize what this was a very brief tour of, hopefully. The point I wanted to try and convey in this talk is that progress is being made in several aspects in terms of broad scale characterization of generic features of vacua. There are many other questions like the topological vanishings and couplings that are being actively studied that I didn't have time to talk about today. But the general broad brushstrokes that I hope to convey are that there are properties of this theory that you can state at a very rough scale that can help you filter through large numbers of possible geometries. And we have come up with consistent frameworks that very readily allow you to access that information. In the case of these topological vanishings that I mentioned, these constraints are ubiquitous. There are, of course, lots of open questions. Can you apply these same techniques to higher order, to non-perturbative contributions to superpotential? The answer is we think so in various contexts. That's for the future. You can ask what happens for dual theories, for example, F theory. Can this be described as a hidden symmetry? These vanishings are very similar in spirit, though not in letter, to certain recent swampland conjectures. And more broadly, when you want to actually push the theory through to a detailed understanding of the couplings, control of the metric is necessary to specify the 4D theory in enough detail. And what we are experimenting with, and we'll have a chance to talk about in the next discussion session in more detail, is that machine learning techniques can provide a powerful new tool in terms of addressing some of these questions that have been serious obstacles over the last 15 years. In particular, we provided the first numeric approximations to SU3 structure metrics. And there are a variety of open questions. For example, what other aspects of the 4D theory that are metric dependent do we want to try and calculate, moduli stabilization, and hopefully we can turn to many of these in the next session. So I apologize for going a minute or two over, and thank you very much for your attention.
Great, thanks very much, Lara. So if you have questions, please raise your hand. There is a question from Chris Krylova in the chat, which was actually about 3 or 4 slides ago, Lara, I think when you first had a graph of the machine learning. Chris asked, what is the efficiency of your loss function, i.e. the percentage of certainty that your result is correct? So it's probably back about 4 slides.
So yeah, to answer that, so the loss here, we're starting out. So there's a variety of different loss functions that we're optimizing. Actually, let me go back one more here. So this loss function, this is for the Calabi-Yau case. So this, in the case of the Calabi-Yau metric heading towards Ricci flat, the axes here, this is about 10 to the minus 1. This is getting very good at low complex structure, and of course, in extrapolation, worse at high complex structure. Various games can be played with this. These numeric approximations, all of them are worse at higher complex structure. But yeah, this is the basic structure. The width of these plots here is the range over the complex component of the complex structure that we're running over. I don't know if that answers your question.
Thanks,
Yes,
Lara. So we have a few
and
questions,
also
hands raised. Can we go to the node from the IAS?
Sure.
In the real world, we'd sometimes like to have very small but not zero Yukawa couplings, for example, to get the electron and light quark masses. So with that in mind, I wonder whether you've tried to figure out if worldsheet instanton corrections turn your vanishing heterotic string couplings into small ones.
That is exactly the hope, right? So just as you said, I mean, and this has been a hope, I should say, as I'm sure you know, for quite a while, is that you can kill off perturbative couplings and then attempt to regrow them non-perturbatively at an appropriate scale. So I think we have thought about that indeed, and in various contexts, people have tried to push this quite far. I should say that a lot of progress has been made in calculating those non-perturbative corrections recently to greater accuracy. So indeed, in a given situation, that would be a promising avenue and an explanation for small numbers. In practice, though, of course, we have to have a fully stable vacuum with the right massless spectrum, and we don't have that yet. So structurally, the short answer is I'm definitely thinking about non-perturbative corrections, and then what types of constraints you can say even at a broad geometric level for those as well. But
Thanks.
Great. So we're short on time, but we have time for maybe one or two more questions. So Miriam has a question.
Yes, actually, it's I have more of a comment, and one is related to the one that Ed mentioned. I do want to mention that sort of interestingly enough, in the globally consistent model that has MSSM spectrum of Bouchard and Donaghy, surprisingly enough, in our work, the R parity violating couplings were indeed zero, but also the lepton couplings were zero. So that's exactly what quantum cohomology should start playing a role in modifying these classical values. And there is actually concrete work more on a toy models done by Katz and Donaghy and company.
I completely agree. Very, very interesting structure and exactly of the spirit of the previous question that you guys found. I'll add there are many, now many other vacua, heterotic vacua was sort of on the similar standing of, you know, control of couplings and properties of the type you mentioned. The question then is, if you need further detail, yeah, how do you filter that efficiently and so on? So, but excellent point.
Thank you.
Great. Okay, so we're just about out of time, maybe 30 seconds for Ivano Basile.
Okay, thank you. I'll be very brief. So I was wondering, regarding extending your methods to more general geometries, right? Wouldn't there be, in general, also the constraint that the metric solve the background field equations, at least to leading order?
Sorry, so you mean beyond the Ricci flatness condition, or you mean the,
yeah, exactly.
the equation?
Absolutely. Well, even the, okay, yeah. Say beyond the Ricci flatness, yeah.
Yes, indeed. So, I mean, one could ask about high order structure. I mean, certainly in the case that I was referring to the SU3 structure, the point is that that is solving the equations of motion for the heterotic string. So the Hull-Strominger solution, you know, to leading order in the theory is the full solution to the equations of motion and specifying constraints on torsion classes. So the examples that we're looking at were of that type, and those are consistent. Yeah, one could ask for different setups in different, you know, compactifications of other string theories or M theory. And from the machine learning point of view, of course, this is all totally generalizable. So doing this for G2 for, you know, M theory, as long as you have conditions on the torsion classes, you can do many different types of G structures.
Right. Thank you.
Okay, great. Thanks very much. So let's thank Lara again. Lara, if you could stop sharing your screen so we can switch speakers. I had a couple of questions, but I'll take those offline.